suppose we have f and g holomorphic on omega, and C is a simple closed curve that doesn't go through any zeros of f. And suppose that the absolute value of f is strictly bigger than the absolute value of g on the curve C, then the number of zeros of f plus g in the interior of the curve equals number of zeros of f in the interior. Okay, so we have some sort of domain like this, and we have a closed curve that doesn't hit any of the zeros of f. It can be some outside, but the closed curve messes them like this. Okay. And we have two functions, f and g, holomorphic on omega. And we're going to consider this thing, f plus g. And we're going to think of this, well, the way to think of this is a kind of perturbation of f. Okay? It's a perturbation of f. Yeah? But it's a perturbation such that g is always less than the absolute value of g is always less than the absolute value of f. Then the claim is that if we change f by adding g, it's not going to change the number of zeros. That's the claim. Okay, so I have set up a demonstration of this. Now, as we've learned, the number of zeros of inside the interior of C is given by the amount of times that f of C winds around 0. Yeah, that's the argument principle that we just learned. Yeah? So if we knew that the number of times that f winds around 0, let me start again. The number of times that f of C winds around 0 is the same as the number of times as f plus g winds around 0, then this is automatically true. Yeah? Because that's the argument principle again. The number of times the image of C under f winds around 0 is the number of zeros inside the interior. Yeah? And the number of times f plus g winds around the image of C under f plus g winds around 0 is the number of zeros of f plus g. Yeah? Yeah? So if we consider this f plus g, and it winds around, and the image of the curve winds around the same number of times as f, then we're all set. Is that making sense, people? Yeah? Give me a thumbs up if so. Cool. All right. So we're going to make life simple, and we're going to think of f as winding around 0 in this very simple way like this. So forget about this for timing. So this is f winding around 0. This is f winding around 0, like this. This is f winding around 0, okay? And 0 here is in the center. Yeah? And then this thing here is f plus g. This thing is f plus g. And the only restriction is that absolute value of f is always strictly bigger than the absolute value of g, right? So this thing is the absolute value of f, right? So this is 0, and this is g, right? And g could be pointing anywhere, but the absolute value of g is always less than the absolute value of f, right? Yeah. So look, so watch what happens as g is doing whatever it wants to do. Like g is going round like this, perhaps. It's going round, like doing this maybe. G could be doing all kinds of weird stuff, going round, circling around, doing whatever it wants, right? But as f is going around 0, then because g is restricted in the way it is, that its absolute value is always less than f, right? No matter what it does, it's forced to go around the same number of times as f itself. Yeah? No matter how crazy g wants to be, if f decides it wants to wrap around twice, right? No matter what g does, it's forced to wrap around twice as well. Start that again. If f wants to wrap around twice, no matter what g does, then f plus g must wrap around twice as well. Do you see what I mean? Yeah? So look, if we start here, then no matter how much g doesn't want to wrap around, no matter how much it resists, it's forced to wrap around as well. Yeah? Is that making sense? Give me a thumbs up if so. Sanka, you okay? Cool. So, our hypothesis that f is bigger than g is exactly the fact that this line, or this piece of string, is longer than this piece of string. Yeah? So the wrapping around of f is forcing the wraparound of f plus g by the same amount. Yeah? By the same amount. So geometrically speaking, we would expect this to be true. We would expect this to be true. We would expect it to be the case that if we consider how much wrapping around f plus g does, it should be the same amount of f. Yeah? Just by visualizing what this hypothesis implies. Yeah? And then by the argument principle, that says that we should have that the number of zeros inside of the interior of C for this function f plus g should be the same as the number of zeros of f. So this statement seems a little bit technical when you first see it, but visualizing it as g being trapped into doing whatever f wants to do, I think kind of makes it somewhat clearer, right? And this is a simplification because I'm just taking f to have like this constant absolute value here. But if I had, you can imagine that if I had a more sophisticated model, the same thing would still be true, right? So long as this is always true, then whatever wrapping around f does, then f plus g must do the same wrapping around. Yeah? Cool. All right. So intuitively, geometrically, we believe this. We believe this. It seems to be true. But we want to prove it. We want to make sure this is what math does. We have our intuition, we have our proof. So, define the following: f of t of z to be equal to f of z plus t times g of z. Okay? So, f of 0 of z is just f of z, and f of 1 of z is f of z plus g of z. Yeah? Then, let n of t be the number of zeros of f of t inside a curve C like this. Yeah. Now claim if n of t is continuous, then theorem is proved. Or proven. Because if it's continuous, then whatever we are at 0, we have to be at 1, right? So if we have a continuous function into the integers, then it has to be constant, because if it's not, then we have a discontinuity. Yeah? Yeah? And it's proven, because if this number changes, if n of t changes, is not constant, then we have a discontinuity. Okay, so it's enough to show that this n of t, the number of zeros of f of t, is continuous. Yeah? 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 But n of t is nothing but the integral, 1 over 2 pi I, integral around the curve of ft prime over f of t dt, dz, sorry. Because that's the previous theorem, that's the argument principle. Yeah, that's what we've learned. And I claim that this thing is a nicely continuous thing. This is a nicely continuous thing. Okay? All right, so suppose we have some sequence tk tends to t tilde. It's enough to show that the limit as k goes to infinity of n of tk is equal to n of t tilde. Yeah, that would be enough. That's exactly what continuity is. Yeah? Well, let's look at these expressions. So look at this. So n of tk minus n of t tilde, what is it? It is 1 over 2 pi I, the integral of c of f of tk prime over f of tk minus f of t tilde prime over f of t tilde, right? Like this, yeah? And we can clean that expression up by having a common denominator, like this. And then we're going to have f of t, f of tk prime times f of t tilde minus f of t tilde minus f of tk over this thing. Oops, the product. Yeah? Everybody happy with this? Yeah? And what we'd like to do is to show that this stuff in here uniformly goes to 0 for all z on the curve, yeah, as we let k go towards infinity. That's what we'd like to do. And let's identify what can go wrong. Well, when we see a quotient expression, one of the things can go wrong is if the denominator blows up. No? But the denominator is not going to blow up. The denominator is not going to blow up because we've set it up so that f has no zeros on the curve itself, and that g absolute value is less than f on the curve. Yeah? And this thing is just a linear combination, not a linear combination, it's just f plus t times g, where t is between 0 and 1. And since g absolute value is less than f absolute value on the curve, then this thing can't mess it up with this thing. So the absolute value of f subscript t is always bigger than 0 on the entire curve. Yeah? Yeah? And in fact, it's bigger than some constant independent of t itself. So notice that absolute value of f of t of z is bigger than equal to the absolute value of f of z minus g of z, like this. Yeah? And this thing, by definition, by hypothesis I should say, is always bigger than 0, and it's a continuous thing, and it's in a closed set, so this is actually bigger than some small delta for all z on the curve C. Yeah? So these guys on the bottom are never going to be a problem for us. They're not blowing up. Their absolute value is always bigger than delta squared, the product of them. Yeah? Okay, so these guys are not dangerous for us. Yeah? Then we have to look at this thing. Well, we have this k thing here, and then this t thing here, and these expressions are different. And the natural way to deal with this is to break it up into two differences where the guy we put in the middle shares one element of each. So what I mean is, if we look at this expression here, so f prime of tk f of t tilde minus f prime of t tilde f of tk, we want to consider something like this: f prime of tk f of t tilde, and let us do this. Let's write f prime of t tilde f of t tilde, and then let's write plus f prime of t tilde f of t tilde. So we'll have plus minus, we'll kill these guys, and then minus this thing, f prime of t tilde f of tk, like this. Yeah, and then we consider, this is a standard trick we do a lot. So we consider this difference and then this difference, and then we'll factor out the common part of each one of these separate differences. So we'll factor out the f tilde from the first thing. So f tilde, like this, f prime of tk minus f prime of t tilde, like this. Yeah, and then we'll factor out the f prime of t tilde, like this, f of t tilde f minus f of tk. Yeah? Cool. And then if we look at this, then these guys are tending to 0. Just by the way we set this up, right? If we take the derivative of this thing, yeah, then as tk goes to t, then f prime of tk plus g prime is going to tend to f prime of t tilde plus g prime. Yeah? So this thing goes to 0, and this thing also goes to 0. Yeah? And this can be made uniform in terms of z because of the nature of these expressions, right? Let me put some more details. So look at this. So f of t tilde minus f of tk, just how we got these definitions over there. Then what's this thing? This is less than, so the f's will just cancel. It's just less than t minus t tilde minus t times g of z. G is a holomorphic function on this closed curve, so therefore it's bounded on this closed curve, so we can make this thing as small as we like, independent of z. Do you see what I mean? Yeah? And if we look at this expression here, f t tilde prime minus f prime of tk, it's almost the same thing, so we differentiate and then we'll have the cancels of the f prime and we'll have this thing here, t tilde minus tk, g prime of z, and again g is holomorphic, g prime is holomorphic on the closed curve, and we have no problems. This is bounded independent of z. Yeah? Cool. So, if we take absolute value signs around this thing, so then we have less than and equal to, absolute value around this, absolute value around this, and then absolute value around this, absolute value around this, which is the same as absolute value this times this, this times this. And we have that these guys here are tending to 0 as tk goes to t tilde, independent of z. So the stuff on the numerator is definitely going to 0 uniformly with respect to z around the curve. Yeah? So the numerator is definitely going to 0 uniformly, and the denominator is definitely bounded above. So this stuff inside the integral is uniformly converging to 0. So we can pass the limit through the integral and therefore have that this thing in the limit is equal to 0. Yeah? Everybody happy? Thumbs up if you're happy. Cool. All right, so the integrand, which is the thing inside the integral, over the curve C, so we can pass the limit we do indeed have that the limit as k goes to infinity of n tk is equal to n t tilde, and we have continuity, and that's all we need. Yeah? So this function, n of t, is a continuous function. Yeah? Into the integers, therefore it's constant, and therefore the number of zeros of f is the same as the number of zeros of f0, because it's by definition, which is the same as the number of zeros of f1 by continuity, which is the same as the number of zeros of f plus g. And that proves the theorem. Yeah? Cool. That proves the theorem.